Hello and welcome to the Chemistry Academy. In this video we're going to go over strong and weak acids and bases in relation to the Advanced Higher Chemistry course. So, brief introduction into what an acid is and what a base is. Now these are the Bronsted-Lowry definitions of acids and bases. You also get Lewis acids and bases, but they are not in the Advanced Higher Chemistry course anymore. They used to be, so you might see them if you're doing old past papers, but they're not in it anymore. So as far as you're concerned, the only definition of an acid and base you need to know are the Bronsted-Lowry ones. So as far as the Bronsted-Lowry definition of acids and bases is concerned, acids will donate protons or hydrogen ions and bases will accept protons or hydrogen ions. Now, the way I remember this, because when I was doing this, I was first at university, because some of you maybe or maybe don't know that I crashed higher chemistry in 6th year and then went straight to study at university, so I didn't do advanced higher chemistry. So when I was learning at university, we had to know the Bronsted-Lowry definition and the Lewis definition, and I was getting confused with them. So to remind myself of the Bronsted-Lowry definition, I imagine a sheep saying bad, so bad with 2 A's. And basically, if you are to write out bad, like a sheep would say it, here's a wee sheep here, then that reminds you that bases accept and acids donate. You just have to remember that's in reference to protons or hydrogen ions. Another good thing to remember, because you are often asked about conjugate acids and bases, conjugate acids and bases are the acid and the base that are made when the other substance or the opposite substance reacts. So when an acid reacts and donates its hydrogen ion, it then becomes a conjugate base. And when a base reacts and accepts a hydrogen ion, it then becomes a conjugate acid. Okay, so the reason the acid becomes a conjugate base is because once it's donated its proton, it's then becomes something that can accept a proton, so it then becomes a base because bases accept. The base, once it's accepted a hydrogen ion, it now has a hydrogen ion or a proton that is able to donate, so it then has become an acid. So the conjugate is like the related, is the word that means kind of related, so the conjugate base is the base that's related to the original acid. So if we look at this example here, this is just generic, got A for acid, B for base. The acid donates its proton to the base, so it becomes A minus and then BH. So then the acid, which was originally A, becomes the conjugate base because it's now able to accept a proton. And the base, which is B, then becomes a conjugate acid because it's now got a proton that is able to donate. So going back the way, this is now our acid, this is now our base. So the acid would become, the base would become the conjugate acid, and the acid would become the conjugate base. Okay? So if we then look at dissociation constants, in fact, before we move on to that, we'll talk about strong acids and weak acids and bases. So the difference between a strong and weak has got nothing to do with concentration. Concentration is how many particles you have in a given volume. When it comes to strong and weak, it's to do with how much dissociation you get. So dissociation is where we have the acid giving away its proton, basically them splitting up into ion form is what dissociation is. For strong acids and bases, you will get full dissociation, so those ions will fully split up and stay separated in solution. Okay, whereas with the weak acids and bases, you'll only get partial dissociation in aqueous solution. So it means some of them will split up into ions, some of them will stay as neutral molecules, and you get like an equilibrium being established. Okay, you need to know which ones are strong and which ones are weak. This is something that you won't be given in the data booklet or anything like that, and they won't really mention it ever in a question either. They'll just tell you what the acid is or tell you what the base is, and you have to know, okay, that's a strong acid, or okay, that's a weak base. So the ones you'll mostly come across in terms of strong acids and bases, for the strong acids you've got most of the common lab acids, hydrochloric acid, sulfuric acid, nitric acid, and then for the bases, basically any of the bases you come across are strong ones like sodium hydroxide. with the exception of ammonia. So ammonia is the only weak base that you really come across. Also, amines can act as weak bases as well. So they're organic molecules that have an NH or an NH2 group. Okay? So you're really looking for the nitrogens to act as a weak base. So they're the main ones. For the strong acids and bases, like I said, you get full dissociation. So if you were to dissolve hydrogen chloric gas in water, it would dissociate into, technically hydrogen ions and chloride ions, but hydrogen ions don't exist on their own in the aqueous solution. They're not stable enough. If you want to know a bit more about that, you can look at my introduction to pH, but we need to be always writing hydrogen ions as H3O positive when it comes to these equations. So as you can see, this is not a reversible reaction arrow, this is a direct reaction arrow, which means there is no, well, they fully dissociate and then they stay as these ions. So that's what happens in the case of all these strong acids and bases. You get the full splitting of the ions. So the sodium hydroxide would fully split up into sodium positive and OH minus. So you get the full dissociation. For the weak ones, like I said, they only partially dissociate in aqueous solution. So some of them will stay as the full molecules and then other ones will split up into the ions. So you get this equilibrium being established. So this is the equilibrium that gets established when you dissolve ethanoic acid in solution. So the ethanoate ion, which is this, the ethanoic acid molecule loses its hydrogen ion to the water, so it gives its hydrogen ion to the water, creating the hydronium ion, and then you get this ethanoate ion, that's what that's called. Then we've got, for ammonia, when you dissolve that in water, you produce NH4 positive. So ammonia is a bit of a weird base because it creates an excess of hydroxide ions because it accepts hydrogen ions. So that's how you end up with alkaline solutions, because it's creating an excess of hydroxide ions because it removes a hydrogen ion from the water molecule instead. So that's ammonium, that's ammonia, and this is the equilibrium that exists between them. So some of the ammonia molecules will stay as ammonia, some of them will have picked up a hydrogen ion from the water and become ammonium. Okay. If we go through some of these and look at the conjugate acids and bases, just to give you a bit more practice on that. So if we look at this one here, this is our acid, okay, because hydrochloric acid is an acid, and then this, in this case, the water is acting as a base. So remember, water can act as a base or an acid. It's quite flexible in that way. So again, if you're wanting more detail on that, don't forget to go and have a look at my pH, introduction to pH video. So this was our acid. It's then lost a proton and become this. So then that's our conjugate base. That's the base that's arisen as a result of the acid reacting. If you're trying to identify a conjugate acid or a conjugate base, sometimes you'll find that one's easier to identify than the other. So just pick the easiest one first. Usually you can clearly see which one's lost a hydrogen ion in the reaction. So that'll be your acid, because acids donate. And then that means by default the other reactant is the opposite. So this would be our, in this case, the water's been our base, and then the hydronium ion becomes our conjugate acid because it's now in a position that it can donate a hydrogen ion. If we look at these ones here, so ethanoic acid is our acid. It then becomes ethanoate, which means that's our conjugate base. And then that means by default that the water was acting as a base and the hydronium then becomes our conjugate acid. For this one here, ammonia is our base. We know it's a weak base. And it's ended up accepting a hydrogen ion. So then that becomes our conjugate acid. So our base has become our conjugate acid. That means in this case water's acted as an acid, and then this becomes our conjugate base. Okay, so hopefully you can see that sometimes it's easier to identify the acid first usually, or if it's ammonium, you know that's a base. And then the chemical that you know most well, if you like, identify what that's doing, and then the other reactant is just going to be the opposite. But just remember the base becomes the conjugate acid and the acid becomes the conjugate base. The last thing I wanted to touch on here was dissociation constant for strong and weak acids. So dissociation constant is essentially the equilibrium constant for these equilibriums that exist for the weak acids and bases. So the higher your Ka value is, the more product you'll have, so the more dissociation there will be. That means that the higher the Ka, or the lower the Ka value, if you like, the weaker the acid or base is, or the higher it is, the stronger it is, like the more dissociation you get. You will need to, if you're asked to calculate the pH of a weak acid, then you need to use this pH equation here, which you'll find in the data booklet. And like I said before, this means you need to know which acids and bases are strong or weak, because you'll just be asked in the question, calculate the pH of a 0.1 mole sodium hydroxide solution or something like that, or calculate the pH of a 0.1 mole per litre ethanoic acid solution. So you need to know, oh, ethanoic acid is a weak acid, so I need to use this pH equation. Or if it was asking you about hydrochloric acid, you know hydrochloric acid is a strong acid, so then you have to use the pH equals minus a half log to the base 10 hydronium ion concentration 1. Okay, so in terms of this equation, the pKa is like what pH is to hydrogen ion concentration. It's essentially the power of the dissociation constant. So it'd be like if you had 10 to the power of the minus dissociation constant, that's what the pKa value is. And then C is just the concentration in moles per litre of the acid. Okay, so you will usually find the pKa value in the data booklet along with the dissociation constants. You'll find that for most of the weak acids and bases. But if it's not in the data booklet, you should be given the Ka value and be able to calculate the pKa using this equation here. Okay, so just remember, it should be in your data booklet. If it's not, if the acid they've told you about is not in the data booklet, then they should have given you the Ka value and you can work out the pKa using that. So you would do this equation first and then plug your numbers into here. Like I said, just remember that your concentration is in moles per litre when you plug it in here. Sometimes they might give you the number of moles and then a volume that's not a litre. So if that's the case, you'll need to work out the concentration first using C equals N over V. Okay, so that is an overview of strong and weak acids and bases and the calculation that you could tend to use for them. So if you go and have a look in past papers, you should be able to find the questions that say calculate the pH of a solution of X and then have a go. But just remember, identify if it's a strong or weak one first, and then you'll be good to go. So I hope you find that useful. If you did, please give it a like. Don't forget to subscribe and tell all your chemistry friends, and I'll see you again soon.